All right, guys. Today I want to talk to you about calculus, and really is an introduction to calculus as it relates to physics. So let's get started. So calculus, calculus. And there's really two major branches of area of study within calculus that'll be affecting us, and those are differentiation you guys will find that I'm a terrible speller, and integration. Okay? So differentiation is really all about finding the slope. Or another way of putting this would be to say the rate of change that is occurring between the two variables in the function. Okay, so the rate of change. So graphically, if we're looking at something and let's just say that, I don't know, ball is being thrown upward and coming back down, so this would be a position versus time graph here. We would be looking at, let's say, the slope at this particular point in time. How do we go about doing that? So what is this slope here? Well, differentiation, or taking the derivative, is going to help us in this case. In integration, taking integrals, integrating a function, is about finding the area under, put that in quotes, under the curve of the function, and graphically. And we'll be looking at this more later. So if we say, okay, we have our, I don't know, doesn't really even matter. Here's our function like this. Again, this is position versus time. It could be anything that we're graphing here, but if I wanted to know the area under the curve in this particular region, from say time 1 to time 2, the way that I will go about doing that is by taking the integral or integrating the function. But again, today we're going to really be starting on differentiation. So let's take a look here. Let's go back to, so we're going to talk about derivatives. Derivative. I really want to start with graphically what we already know about position, velocity, and acceleration functions graphically. So let's look at a position versus time. And let's take a velocity versus time graph. And acceleration versus time graph. Okay. So let's say that we just have a, I don't know, constant acceleration. Looks something like this. And if we were to track this slope here, we know some things about the position versus time graph as it relates to velocity versus time graph. Number one, we have a curve here, so we know that we have acceleration occurring, and that the slope of our position versus time is going to tell our velocity with respect to time. Well, if I'm tracking this, looking at the slope of this line here, and it's going to continue to increase, and it starts out essentially horizontal there, so I know that my initial velocity at time equals 0 is going to be 0, and then I have a constant rate of change here that is occurring. Potentially, I don't know what this is. I mean, I didn't give you the exact equation, but qualitatively it's going to look something like this. And this is graphs that we're very familiar with. And if my velocity is changing at a constant rate, we also know that the slope of a velocity versus time graph is going to tell us our acceleration. So this is a positive constant rate of change, a slope here in the velocity versus time, which would give us an acceleration versus time graph that looks something like this. Now, as it turns out, what we're really talking about here when we said the slope of these graphs is the derivative. Okay, or it's if we were to differentiate the position versus time function, we would get the velocity versus time function. And the same thing is true here. If we differentiate or take the derivative of the velocity versus time, we will get the acceleration versus time function. Now, up to this point, when algebraically, we've been holding off on doing anything other than constant acceleration, either zero acceleration or constant acceleration. Well, now using calculus and taking derivatives, we can analyze functions that don't have constant forces or constant accelerations occurring with respect to time. So that's one of the benefits of being able to utilize calculus above and beyond, one of many, in comparison to algebra. So the real question, though, what I really want to dive into here is, well, when we look at this, how do we take the slope of a line? Well, if we had a function, let's say here, that was just, all right, let's say that this is x is a position, a function of time. Let's say that this is 3. We're going to say that this is 2t plus 3. And if this was our function of position versus time, hopefully you would remember that, well, at time 0, I'm at position 3. So this really is my initial position here. And the slope here, again, this being in y equals mx plus b format for a linear line, is that this m2 is going to be a slope here, in which case I would get a constant slope. And it's pretty straightforward in terms of how we are comfortable at this point in being able to determine that the velocity, which would be a constant velocity, it would be 2, and we would have, you know, a velocity graph that would look something like that at 2. But we do know qualitatively that we need to find, how do we find the velocity on a curved line on a position versus function, position versus time function? So we need to take a tangent line. Well, taking a tangent line of a circle, you can kind of make it perpendicular, and ultimately we need to be perpendicular to the curve, but it's very hard to actually do that. So graphically, what we've been doing or saying is that if I wanted to know what is my velocity rate at that particular time, at some time t1, I know that it's a tangent line, and I can draw this line and approximate it as best I can, but how do I actually find this tangent line with specifically, okay, at that particular time? Well, that's how we're going to do it. So how do I find the tangent line? How am I going to do that? Well, that's really where the derivative function comes into play. All right, so here we are again, derivative. Let's start with a position versus function graph to kind of work through this. I'm going to make this a little bit bigger here. And let's say, again, we have, all right, where we're going to say that this is x equals t squared. Now, if I wanted to find the velocity right here, and we're going to call this at t1, how would I go about doing that? Well, let's look at it and say, well, I'm going to analyze this motion of this object over t1 to t2. I wonder if the screen just blanked out there. That's great. All right. So how would I approximate the velocity here? Well, we have average velocity, right? We have an equation for average velocity, which is what? Well, it's the change in position over a change in time. So if I were to draw a straight line here, let's see if we can get this. Okay, if I draw a line between these 2 points, I can get a slope off this line. Again, it's delta x over delta t. And so we're really talking about this time period here as my delta t. And if I were to look at these correlating positions, x1 and x2, well, this really here is my delta x during this change in period of time. So if I know these two different points, I could find them. If I knew the function here and I knew these particular points in time, I could go about solving for the average velocity over that entire period of time. But that really doesn't give me what is my velocity at time period 1. What is it right here? Well, intuitively we know, because of what we've already, your prior knowledge about the tangent line is going to give us that instantaneous velocity as opposed to average velocity. We need to find this tangent line. And again, I'm eyeballing here what is the best tangent line. But what you can see, for us to do that, we have to actually bring this change in time period smaller and smaller. So if I were to look at a time period here versus a time period here versus a time period here, what's happening is that my time period is getting smaller and smaller and smaller. And so these lines, as I were to connect these two lines, are coming through these different points, and I'm getting ever closer and closer to my tangent line. So this equation would work as I continue to drive this delta t smaller and smaller and smaller and smaller. And in math, we call that taking the limit. So really what we want to do is look at this equation and say, well, if I want to know my instantaneous velocity, I need to take the limit as delta t. Oh, I don't know why I divided that there. It's just really just the limit. As delta t approaches 0 of the rise over the run. And so what is this change in x that we have here? This, by the way, is called the limit process. Okay? So I'm just showing you this process. You will not have to be doing this, but it helps to come from our understanding of what we understand about average velocity and think through this as we change this delta t smaller and smaller and smaller. We can see the slope getting closer and closer to what we really want is the tangent line at that particular point in time 1. So the limit process here, how do we solve for this change in x? Well, x is really a function of t, okay? And so this particular point, if it's x2 minus x1, well, x2 is really function of x with respect to t plus delta t. So let's just say if this was time was 2 seconds and this was time was 4 seconds, then I would need to know the function, the x position at time 4 minus the position at time 2. But I could write it in as t1, or the time that I'm looking to find it, plus t2 would equal that. So if that would mean that in this case delta t would be 2. But if I'm leaving it in variable form to find x2 minus x1 for the top part of this equation, the way I can really write this is to say x as a function of time, this is time 1, the time that I'm looking for, plus the change in time, that's this really overall is x2 here, minus x1, which is really just the position of x with respect to time at time 1. So this is really x1. Okay, so x2 minus x1 all over the change in time. So this limit function, and we're going to analyze this function as it relates as we take delta t closer and closer to 0. So let's put a pause in this for a second. This is the function. Let's analyze this for a more simple graph than this. Let's just look at a simpler one. If we just were to say, let's just take these two here, and so that x is equal to 2t. Right? So we're still doing position and time. X equals 2t. If I were to apply this function here, the limit, if I wanted to find the slope. Now, we all know this is a linear line here, and this is really just the slope here is 2, but let's use this equation to validate what we already know about a linear line on a graph. So I'm going to take the limit delta t as it approaches 0 for this function here. So x is 2t, but I'm not going to put 2, I'm not going to put t, I'm actually going to find t plus delta t. So the function of t plus delta t is going to be 2, and then instead of t, we're going to substitute t plus delta t. So t plus delta t minus the function itself, which is just 2t, all divided by delta t. Well, let's distribute this 2 out. So we have 2t plus 2 delta t minus 2t over delta t. Well, positive delta t, 2t minus 2t, if I divide up by delta t, I'm left with this being equal to 2, which this is the slope. That's what we solved for. So the limit of this function, which is really just the change, the rise over the run, in this function here gave us a slope of 2, and it's 2 throughout the entire range of time. So that's true there. Well, what if we apply it to this function here, x equals t squared? Let's see how that looks like. By the way, this limit of the rise over the run, this really is the derivative. This is the slope. It is the derivative. That's what we're talking about here, okay? It's finding the slope of a function. And the way that we write that is actually d, in this case dt. So what we're really saying here is we're going to take the derivative of the x function or position function with respect to time. That's how you say that. So dx dt is the derivative of the position function with respect to time, which in this case, again, we're just working on the limit aspect of things as delta t approaches 0. Again, we're going to now take and add in and look at our function t squared. So we're actually going to say, well, t plus delta t squared minus the original function with respect to time, which is t squared minus t squared all over delta t. All right, so we got to take care of this, square this out. So I'm just going to move over, give myself a little bit of space. So square it, t squared, and then we have a t times delta t, so that's 2t delta t plus delta t squared minus t squared, again, all over delta t. Well, let's see, we got t squared will cancel out with negative t squared. And now I'm going to divide through, so this delta t can go away, and I can get rid of one of those. So we're left with 2t plus delta t. And remember, we're taking delta t as it approaches and goes to 0. So if delta t goes to 0, what we're left with, so dx dt for this function, x equals t squared, is just 2t. What is this saying? This is saying that the velocity at any one point along here is going to be 2 times the time. So if I wanted to know the slope of the tangent line at time equals 2, I plug in 2 for t, and I get a slope of 4. What if it's time equals 4? Well, if time equals 4, my slope would then be 8. And that makes sense as I look at and track that as time goes on, every second I'm doubling the slope or doubling my speed as it relates to a position versus time function of t squared. All right, so hold on to this for this particular function. We'll kind of come back to this. So this is the limit process. But what we're really going to be using, we're not going to do this anymore. Okay, this is just so you can understand and make the connection. And you'll spend a lot more time in calculus class going over this as that time approaches 0 and taking the limit aspect of things. But really what we're going to be functionally using is the power rule. So let's take a look at that.